In this demo, we are going to present the work on discover, provision and orchestration of machine learning inference services in a heterogeneous edge. Looking at the literature of machine learning research in distributed computing system, we realize how there are different areas that are very well researched, including optimizing machine learning training performance and machine learning inference latency, model selection policies based on machine learning model performance, distributed training, and federated learning. However, there is limited applied research in the context of machine learning inference provisioning in distributed edge-based systems. From distributed edge-based system perspective, very simple scenarios were considered. For example, not many scenarios where multiple edge nodes are involved, and also hardware heterogeneity and networking aspects are often not considered. From this point of view, machine learning inference research faced new challenges in terms of optimal service provisioning and resource allocation in distributed edge-based system. Looking at the whole picture, the system we would like to analyze looks like this. We have a cloud facility, multiple edge nodes, and several end devices that are benefiting from the provisioning of machine learning inference services. The research question that we would like to answer with this work is how can we ensure an optimal trade-off between machine learning inference accuracy and machine learning inference service provisioning distribution in heterogeneous edge-based systems? In terms of challenges and requirements, considering realistic and more complex IoT deployment scenarios, there are additional requirements to be fulfilled. For example, we would like to have a sort of plug-and-play interoperability among edge devices embedding different AI accelerator. We would like to have an agnostic machine learning inference service discovery and provisioning, and we need combined computing and networking aware orchestration mechanism suitable for satisfying the quality of service of AI-enabled applications. But in this context, what is a resource-constrained edge node? In this slide, we are presenting the hardware characteristic of the devices that we have been using in our deployment. As you can notice, the three devices are using three distinct AI accelerators. In the case of the UP2 AI Edge X, the Visual Processing Unit, VPU. In the case of the Jetson Nano, the Graphic Processing Unit, GPU. And in the case of the Coral Dev Board, the Tensor Processing Unit, TPU. You can also notice how the three devices embeds different characteristics also in terms of memory, storage, connectivity, and CPU. The hardware heterogeneity is reflected also from software perspective. In fact, each board has a different software pipeline for compiling the machine learning models, and this implies also that the machine learning inference latency varies from board to board according to the compiler parameters. The main implication of this aspect is that if we take the different devices out of the box, we really can make them talk between each other as they have different software pipelines. But what we are looking for is to develop a software architecture that makes the different devices talking between each other in an agnostic way. Along with what discussed earlier, when we want to study machine learning inference provisioning in distributed edge computing system, we must take into account additional aspects, including the edge node resources, which means the computational capabilities available in the different nodes when operating, and the network performance in terms of latency and bandwidth. Because in the scenario that we are trying to analyze, the question we want to answer is which edge node can provide better inference to the end device? In order to address the challenges and the requirements introduced earlier, we came up with a software architecture that is depicted in the following slide. For the purpose of this demo, we are going to focus on the inference provisioning management and, more specifically, on the capabilities that the inference agent is able to provide. These are the main system architecture features that we are going to showcase in our demonstration. First, the DNS-based inference service discovery. Through DNS queries, an end device can easily discover what are the machine learning inference services that can be provided by the edge devices cluster. This is done agnostically respect to the edge node's hardware characteristics. Then we are going to introduce the concept of health checks. Through the health checks, it's possible to define what system and application parameters can be considered healthy or not. And running recurring checks allow to ensure that the system performs the way it's expected, as well as to orchestrate allocation and provision of the inference request based on the availability of computational resources of the nodes. Then, the inference service execution migration. The proposed and deployed approach allows orchestrating the migration of the machine learning inference service execution across the different edge nodes in near real time based on the live available computational resource of the nodes. Finally, the inference pipeline components migration. When the requested services is a composition of multiple inference services, components of the model's pipeline can be offloaded between edge nodes, still based on the live available computational resources of the nodes. Here we introduce the testbed and the demo scenario. The edge side is composed by the device introduced earlier in this presentation. We have 3 UP2 AI Edge X, 1 Coral Dev board and 1 Jetson Nano. The first architecture feature that we are going to showcase is the DNS-based inference service discovery. From the terminal of our end device, the Raspberry Pi, we are going to write a DNS query that looks for an inference service of object detection, in this case defined as OBJT. Once submitted the query, the end device will receive a DNS response from a customized DNS server with a list of the healthy edge nodes that can, in that moment, provide the object detection service. The second system architecture concept that we want to showcase is the health checks. As you can see, health checks can be easily registered through a JSON file and defined, for example, with a bash or a Python script. In this example, we are registering and define a memory RAM health check. Specifically, we have set 2 different thresholds above which the system will enter in a warning or critical state. If an edge node enters in critical state, it won't be considered anymore a suitable node for the provisioning of services. Both DNS-based inference service discovery and health checks rely on the use of Console, which is a service mesh solution that provides multiple control plane solutions. We are now going to show in practice how the health check concept works. From the terminal of the end device, we are going to make a request for an object detection service. As you will see, the response comes from one of the UP board that belongs to our cluster. Now we are going to log in this UP board and add some fake stress on the CPU of such device. Once the device gets overloaded over a certain threshold, the CPU health check will trigger the critical state. The consequence is that if we go now to make again a request for an object detection service, we will receive the response from Coral board, while the UP board will remain unavailable as long as the overload status persists. Finally, in the last part of this presentation, we are going to analyze 2 different use cases for showing how our system is able to orchestrate the migration of the machine learning inference service execution across the different edge nodes in near real time. In the first use case, we use an object detection application and we will show how and when the execution of the service can be migrated from an edge node to another. In the second one, we refer to the particular case in which the requested machine learning inference service is a composition of multiple services creating together an inference pipeline. As shown in this slide, the pipeline is composed of 5 models and it uses a face detection algorithm as core component of the entire pipeline. In this part of the demo, we are going to show how the design system can move the inference execution to the healthiest node of the cluster as soon as a local overload occurs and by considering the available computational resources of all the other edge nodes. Referring to the scenario of inference pipelines management, we demonstrate how to seamlessly split the execution of inference pipeline components among different edge devices. In this specific demo, we only utilize 2 UP2 AI edge boards, and we display how, as soon as the device running the whole pipeline gets overloaded, the pipeline execution will be automatically split among 2 different edge devices. This concludes the video presentation of this demo. Thanks for your attention and looking forward to discuss more about this project.